Hello, I am Daniel Lee, and this is my video report for Lab 4 Oscillations for Physics 2211. The purpose of this lab is to evaluate an oscillating spring mass system in which the mass swings in an arc-like pattern and to determine its relation and application to the energy principle. Here are three important aspects of my video that I'll discuss today. Firstly, there are two main forces at play within the spring mass system. The spring force, which is derived from Hooke's law, is equal to negative k times s, where k is the spring constant and s is the spring's length, subtracted by the spring's relaxed length. The momentum principle, which is derived from Newton's second law, allows us to utilize the velocity and position update equations in order to compute energy and position changes. The energy principle states that the changes in energy is equal to the total work of the surroundings. In this spring mass system, the three forms of energy present include the kinetic energy, gravitational potential energy, and spring potential energy. Kinetic energy can be found through 1/2 times mass times the velocity squared. Gravitational potential energy is mass times the gravitational constant times height, and spring potential energy is 1/2 times k times s squared. Here are some important principles that I would like to discuss and expand upon. Firstly, the forces within the system act in different directions. Gravity acts down while spring force acts in the upward direction. These interactions have effects on momentum, velocity, and position. An important note of the change in energy is that it is equal to 0. This is because I have chosen the surroundings to be nothing while the system to be the spring, mass, and earth. The results of the lab are that the energy principle applies and the period of oscillation in x is 1.614 seconds and 1.329 seconds in the y. Here's a method or process I went about in this lab. First, I established the process that I was going to use and the video and tracker. I analyzed the forces present in the video and performed the subsequent actions. Second, for the glow script code, I changed the values and applied the ideas of forces and energy to the code through the gathered data. Third, I analyzed the code and ran it, and then I got the graphs and I used the graphs to answer the questions that we were given. Here are the initial conditions for my code. The mass of the object was given as 0.402 kilograms and the initial position was found through the tracker data. Delta T was found appropriately to match the total time of the recording of the system, as the system was in action. Appropriate constants are found such as G and LO, the relaxed length of the spring. The spring constant K was given as 6.83. S is found by first finding the length of the spring and then subtracting that by the relaxed length. The energy calculations with their subsequent formulas are given, and the total energy is the sum of each separate portion. Again, the system is the spring and the mass and earth, while the surroundings are nothing. Here's the code used for each iteration. I update the initial energy conditions each time. I compute the force gravity through the minus mg formula and the spring force through the minus k times s times l hat. Then I add the two forces to find F net. I use the velocity and position update formulas to update the respective values of the spring mass system. I then update the spring length and motion, and then update the change in each type of energy. Here are the results of my code. The blue demonstrates the change in kinetic energy, the red shows the change in gravitational potential energy, the green shows the change in the spring potential energy, and the orange shows change in total energy. The total energy is the horizontal line at the 0 mark to show that the energy conserved and the energy principle applies. Here are other graphs of my experimental versus model positions. The left shows the x position and the right shows the y position of the system. The lines are not the same since the code simulates an ideal environment while the experimental code accounts for other forces such as drag. Thus, this could be a source of error within my code, or not my code, but within the experimental data. The first what does it mean question is whether the energy principle is satisfied. So in this situation, yes, it does satisfy. This is because there is no work done by the surroundings. Thus, since the change of energy is equal to the work done by the surroundings, the energy principle is satisfied. In the graph, delta E remains at 0 throughout the time period in a horizontal line. The second what does it mean question asks to compare the estimates of oscillation periods. So using the formula T, which is period, equals 2 pi square root m/k, I found that the period of oscillation of x equals 1.614 and the period of oscillation y is 1.329 from the estimations in my graphs. Some factors that could have effects are drag, friction, and other gravitational forces to skew data. From the equation, period inaccuracies can result in variations in spring constant, thus affecting other quantities such as spring potential energy and spring force. Thank you for listening.